So let me give you an example of what we were talking about in the previous video. Right? So in the previous video, we introduced step functions, and then we showed that in particular, well, first we showed what the Laplace transform of a step function is, right? It's really easy to calculate. And then we talked about how in practice we're going to be working with functions of the form like this. More general, but for now, something that looks like this. G of t equals 0 for t less than c, and f shifted to the right, c units for t greater than or equal to c. Right, what that means, so let me show you graphically. So what's the difference between doing something like this, where g of t equals 0 for 0 less than or equal to t less than c, and just t squared for t greater than or equal to c? Right, this is not what we have. Right, notice because I'm not shifting the function here. So here I'm working with the function t squared. Right, so it's a regular quadratic, t squared. Notice, however, that I'm not, oh, let me make this more specific. Let's say 1. Yeah. So notice here that I'm shifting, right, here by 1, or I'm turning on my function at 1, but I'm not shifting my function by 1. Okay, so this is not something that looks like what we have above. So let me write something that actually looks like what we have above. So if you have something like the same thing, 0 for 0 less than or equal to t less than 1, and then this square function, t squared, but shifted to match the whenever we turn it on. So let's graph both of these and see what they look like. Right, so one of them is 0 up to t equals 1, and then at t equals 1, it becomes t squared. But it's not shifted. Right, so meaning that at 1, t squared equals 1, so this function would start here, and it looked like a quadratic. This is without the shifting of the function f. Right, so this is just f of t equals t squared, without shifting. Now, in the case that we're shifting, so like we have in this case, again, the function is 0 all the way till t equals 1. Now at t equals 1, it becomes t squared, but shifted to the right 1 unit. So we would be starting at 0 like we would if we were starting to graph our function here for t squared. And it will look like that. So you can see that there is a difference if we write it with a shift or if we write it without a shift. So it's not the same. So that's what I mean when I say that for g of t, we're starting f at t equals c, right? Meaning that we're doing something like this instead of something like this. So that's the idea. You want the shift to match when you are switching on the function. Okay. Now let's do a note. As I said, the point of introducing these step functions is being able to simplify the computation of the Laplace transform, right? So we don't have to use this full definition with an improper integral. So notice that if we have g as before, right, where g of t equals 0 for t less than c, and f of t minus c for t greater than or equal to c, so again, the same interpretation as before, then we can actually write this simply as u sub c of t times f of t minus c. And we can verify that this is correct. So let's see what this function is. Right, so u sub c of t times f of t minus c. Now, this is equal to, for t less than c, what is going on? Right, for t less than c, u sub c of t is 0, and this is just the same, f of t minus c. Right, and that, of course, just becomes 0. Now, for t greater than or equal to c, u sub c of t becomes 1, and this, of course, is just the same. And you see that this is exactly the same as g of t. Right? So using step functions, we can rewrite a piecewise function as a product of a step function times a shifted function. Right, so that's the first useful thing that we're going to use. Now, since we want to be taking the Laplace transform of this product of a step function times a shifted function, where the switch matches the shift, right? Well, that's important, right? We talked about in the previous 2 slides. We want to be able to calculate the Laplace transform of this. It turns out that there's an easy definition for this Laplace transform. Right? So if the Laplace transform, big F of s, of a function f of t exists for s greater than a greater than or equal to 0, which again, remember this a came from the exponential order. And if c is a positive constant, right, so if c is greater than 0, then the Laplace transform of the product of u sub c of t times f of t minus c is just equal to e to the minus cs times big F of s. So an easy formula, an easy computation for the Laplace transform, right? And you can show this easily, right? You can go through the actual calculation, right, using the definition of the Laplace transform, and you get this easy formula. Moreover, right, assuming that f is continuous, right, so we're restricting the domain of the Laplace transform to continuous functions, then we have this Laplace inverse definition as well. Whenever you have e to the negative cs times big F of s, you can take the Laplace inverse of that. You get only one solution, and it's the original thing, u sub c of t times f of t minus c. So again, whenever you have a piecewise function, as in this example, where the shift matches whenever we're starting or switching on, right? So our shift c matches whenever we're starting, so at t equals c, then we have this really nice formula. First of all, we have this really nice formula to write g of t as a product of a step function with f shifted c units. And again, this c's have to match. And from that, we get an easy calculation for the Laplace transform. Now let's see an example. Let's find the Laplace transform of f of t, where f of t is given by 0 for t less than 2, and t minus 2 squared for t greater than or equal to 2. Now notice that this function has the right form, right? Because it's being switched on at t equals 2, and that matches the shift we're applying to the function. Right, so think here as we're working with the function t squared, and we're shifting it 2 units to the right. So everything matches. That means that we can write f of t as just u sub 2 of t times what? Well, going back to our note, times f of t minus c. Okay. So f of t minus c in this case is this part. We're shifting the t squared function 2 units to the right. Right, so this is just t minus 2 squared. Okay. And now, when we take the Laplace transform of this, so Laplace transform of f of t is the same as the Laplace transform of u sub t of t times t minus 2 squared. And by the theorem we saw in the previous video, this is just going to be e to the minus cs, or c is the shift, times the Laplace transform of the unshifted function. So by definition, this is going to be equal to e to the negative c, which in our case is 2, times s, times the Laplace transform of the unshifted part of the function. So the Laplace transform of t squared. We have a formula for this. Right? If we go back to our notes to theorem 1, and this is then going to be 2 factorial over s cubed. Oops. Yeah, so this is going to be equal to, so the Laplace transform of t squared is just 2 factorial, which is just 2 over 2 cubed, over s cubed, sorry. Now you see how easy it was, right? We didn't have to do the actual definition, using the improper integral, all we have to do is first make sure that the c value in which we turn on our function, which in our case is c equals 2, matches the shift we're applying to the function inside here, right? In this case, the function is t squared, and we're shifting it 2 units, which matches the c when we turn on the function, right? That means that using the node, using the node 2, we can write this function here as just u sub 2 of t, right, where 2 is just a shift, times whatever shifted function we have, which is t minus 2 squared. And then by theorem 1, the Laplace transform of this product is just e to the negative cs, right, where c is 2, and I wrote it as 2 instead of as c instead of 2, right, times the Laplace transform of the unshifted part of the function, right? But where shifting is t squared, right? So that's the unshifted part. Right, so it becomes the Laplace transform of t squared, which we can just look up in our table. And this is how working with step functions can allow us to efficiently calculate Laplace transforms whenever your piecewise function has this nice form.